Did you want to try share your screen?
Yes. Can you see my screen?
Yes, we can.
So you know how much I did. And then you know what, like Frank, I'm all upstairs, you know.
All right. Hello, everyone. Hope your reading week was restful. Welcome back to the Civil Seminars. Just a little bit of housekeeping. I've been notified that the 3-minute thesis is actually mandatory for all MESC and PhD students, regardless of if you presented at a conference or not previously. So if you're graduating soon, please sign up for the 3-minute thesis for April this term, okay? Other than that, today's speaker is Silvana, who received her PhD from Western under supervision of Dr. Lowe. She currently works at EXP, which is located in London. And she's kindly agreed to give a talk today on the swelling potential of shales. So with that, please, everyone, warm round of applause for Silvana. Thank you for coming.
Hello, everyone. I'm pleased that I got a chance to present this topic to you, which is a pretty hot topic in this part of Canada. I will talk about swelling shales and how a methodology, which used when is used when you dealing with this kind of shales during the design and build of underground structures. So the outline of the presentation today is I will talk about properties of shale and engineering issues faced during the design and construction of underground structure in this rock formation. I will talk about swelling mechanism, explain why that shale swell. I will talk about laboratory testing and time-dependent deformation, which is a swelling parameters, what we obtained from this laboratory testing. And then how these results of this test can be used or applied for design of underground structures. At the end, I will talk about one case history, which is the Billy Bishop Pedestrian Tunnel in Toronto, which connect the mainland and Billy Bishop Airport on the Toronto Island. So you guys, you're probably familiar with the Geology of Ontario. We know that Canada is geologically one of the oldest countries in the world, and half of its territory is actually exposed Precambrian igneous and metamorphic rocks, which is 4 billion years old. In Southern Ontario, actually we have unexposed Canadian shelf, which is where the Ordovician sedimentary rock, 500 million years old, is on top of this Precambrian igneous rock. And that Ordovician sedimentary rock consists of shale, dullstone, limestone, and sandstone. Shale represent the accumulation of marine mud. This figure down actually showing the geology profile in Toronto area. And you can see that in Toronto area, there is a Georgian Bay shale, which is on the surface. And most of underground structures in Toronto actually is placed in this Georgian Bay Shale. Or if we are in Niagara area, that it's Queenstone Shale. So the properties of these shale is that they are generally massive sedimentary rock with sub-horizontal bedding planes and relatively widely spaced or no vertical joints. And occasionally there are rubble zones at the weathered rock level. Usually the surface of this rock is very weathered. This rock is interbedded with the layers of limestone and sandstone. Sometimes there are some clay seams in upper levels. This rock has locked very high in situ horizontal stresses. K0 could be 4 or even greater. This is relatively weak rock. It has a brittle failure in unconfined compression. The rock has very low tensile strength, less than 10%. This rock is also characterized by highly fissile and susceptible to the slacking and disking along the bedding planes upon exposure. Here in this figure, this photo, you can see that disking along the bedding planes. That rock has relatively high salinity in rock pore water. This is important later on. I will explain why it is important from the point of swelling mechanism. And the major characteristic of this rock is that time-dependent deformation behavior upon relief of initial stresses. So when we excavate, tunnel or any structure in this rock, this time-dependent deformation behavior start in this opening. Usually that vertical swelling potential is higher than horizontal. And the other characteristic that is time-dependent deformation, highly stress-dependent. Later on, I will explain why these characteristics is important for the development of methodology of investigation and design in this rock. So this figure, these photos, they show Georgian Bay Shale cores recovered from the ground at different depth, 20 meters, minus 3 meters below the bedrock surface, and 500 meters below the bedrock surface. You see here, it's a massive rock, sedimentary rock with limestone interbeds. This is from the, as I said, at the top close to the bedrock surface. Usually this rock is weathered and some clay seams could be found. This core from this depth usually is also solid initially, but when you bring it up to the surface, it's just start disking like this and behave like this. So what is the problem here? What are engineering issues on excavation in this shale? Depend on type of the structure, could be open excavation or could be tunnels. It should be short-term engineering issue during construction or long-term during the use of the structure. So during the construction in open excavation, what's happening, we can see heave and buckling of floor. And also we can maybe see movement along bedding planes. In long term, beside these two movements, we can see some long-term deformation in unsupported excavation or stress increases in structure elements, potentially leading to distress. So if we have a wall, a joint adjacent to the rock, we can expect stress increases in the structure element, which can cause distress. When we're talking about tunnels, tunnels are completely surrounded by rock, and there during construction, we can see movement along bedding planes at or near spring line of the tunnel. then we can see local failure at the crown and invert, or some invert heave. In long term, depending if the tunnel is lined or unlined, so if it's unlined, we can see some displacements increase, invert displacement with time. If there is a liner of the tunnel, then we can maybe see the distress of the liner due to stress increase. So in following slides, I have a few examples showing these engineering issues. One is heaves of excavation floor. You see here and here, you can see how big that heave is here in Duffrey Inquiry after excavation. Then another example is cracking of Thorold tunnel wall. This tunnel is built under the Welland Canal in Thorold, and it's built from 65 to 67. So you can see this is the cross-section of that West Service building. And so after several years, what happened? This wall cracked here, even though the wall was almost 3 meters thick. So in 1971, these cracks appears here, and everybody was confused because they knew that the tunnel was properly designed and built. And then I excavate behind this wall, and then they find shale zone here. So they find shale exactly at the level of these cracks. So this is actually beginning of this story about creating methodology for investigation and testing this swelling rock. The next example, which what can be engineering issue in this kind of rock, is this roof failure in Niagara Tunnel. Niagara Tunnel is 15-kilometer long tunnel, which going below the Niagara this is the intake above the falls and going below the city of Niagara Falls, and going up outlet is at Sir Adam Beck generating stations. This tunnel is supposed to be circular because it's excavated by big, huge TBM machine. And you see, but you look, the machine is somewhere there. So after excavation, because of this is in Pinston Shale, this isn't anymore circular. It's become like a horseshoe. And actually, what does that mean when they notice that this happening in the Pinston Shale? They changed the alignment of the tunnel. Initial alignment, the red part is Pinston Shale. So they had, this is the tunnel alignment, initial one. And they had to go below this St. David Gorge. So we're talking here about 140 meter deep tunnel. And once when they get here in Pinston Shale, they had the problem like this. So when they realized that the problem was in that swelling, stress relief, deformation and swelling, they get out from Pinston Shale as soon as possible. So the new alignment was like this. So that's what can happen when you put your structure in this kind of shale. So for design and construction of underground structures in swelling rock, it is important to understand initial stresses and time-dependent deformation behavior of rock mass. And then to develop stress-strain time relationship for the analysis of rock structure time interaction problem. And also to develop strategy to address these issues in design. So, so that's the major thing to understand this, and also then to develop this methodology, how to analyze this rock structure time interaction problem. Swelling, now why this rock swell? That's the question, because usually we know that clay swell if it has a montmorillonite or any other kind of swelling minerals. As I said before, shale is actually cemented clay or mud. So the major particles are clay particles, but these particles in Georgian Bay shale and the Queenstone shale, they don't have any swelling minerals. They don't have any montmorillonite or any swelling minerals. So they were puzzled why this rock swell. And the easiest explanation is because of process of osmosis and diffusion. Actually, when this rock was and this clay is deposited and rock formed over the long geological time, this salty water stayed captured into the pores of this rock, and so that the pore water in this clay, in this shale, actually is very salty. So when that rock gets in the contact with the fresh water, we have a process of osmosis, movement of ions from the higher concentration to the lower concentration, and movement of water molecules from the higher concentration to the lower concentration. So since water molecules are big and pores of rocks are small, when water gets into the rock, it needs space, so it's increased the volume, which is actually swelling. So in practice, to have swelling, we need to have the access to the fresh water, and we need to have that outward salt concentration gradient from the pore fluid rock to the ambient fluid. For example, in this Niagara tunnel, we actually bringing the fresh water from the Niagara River 140 meters down in Queenstone Shale, which has very high salinity. And bringing that water from the fresh water down actually caused the swelling of that Queenstone Shale. On the other side, as I said, the shale is formed by cementing of clay particles. So from the soil, it becomes weak rock. These clay particles are cementing with some cementing agent. Queenstone Shale and Georgian Bay, they are cemented with calcium carbonates. So if this bond, interparticle bond, is very strong, there is no swelling. Yeah, but if it is weak, then this osmotic pressure is higher and we have swelling. So that's important to see if rock has, what is the calcium content in that particular rock, which forms that cementing bond. So a methodology for the investigation testing of swelling properties of shales and shale formation was developed in 70s after that problem in Thorold tunnel. It was developed by Dr. K.Y. Law from this Western University. And since then, this methodology has been adopted by the industry and is used for design of underground structures in Canada and around the world. In this map, it's shown some projects which used this methodology for design. Beside Canada and US, we project in Peru, Chile, Qatar also use this approach for design of tunnels, and excavation in shale, in swelling rock, let's say like that. If you work in Ontario, you are probably in Toronto. Tomorrow, as a geotechnical engineer, you are probably will be involved in some underground structures, and if those structures are placed in these shales, you have to apply. You should apply this methodology. It's almost become standard in this area. So this methodology include two steps: site investigation and laboratory test. Site investigation is actually measuring rock coring and obtain a rock cores for testing, and also in situ stress measurement at the site. Once when we have this rock cores, we do two types of tests: strength to measure strength and deformation, and also swelling. These parameters obtained from these strength tests, we use to estimate stability of that excavation and to propose some support if it is required. The rock cores obtained from the ground are suspected to swelling test, and then using this parameter obtained from this test, either using a Lowen-Yuan model or Lowen-Hafning model, we can predict some behavior of that particular rock at that particular site. Once when we have that, we can make some kind of decision on method of accommodating time-dependent deformation. And I'm going to talk in this presentation more about these parameters to obtain and these design models, as well as a method for accommodation of time-dependent deformation. Method of laboratory testing of rock swelling includes several tests. One of them is free swell test, which is designed to evaluate free swelling behavior of rock in all directions. The second test is semi-confined swell test to evaluate the stress-dependent swelling behavior of rock, because I said that this rock is stress-dependent, and the swelling behavior actually is stress-dependent. And third type of swell test is Null swell test, which is designed to measure the critical pressure required to completely suppress swelling of rock. What does that mean? If you have your structure, tunnel liner, for example, directly on the rock, because the rock swell, it exhibits some critical pressure. Put the pressure on your structure, and we can, using this test, we try to measure that suppression pressure. Besides that, we of course measure calcite content to explain mechanism of swelling. If the calcite content is high, probably that rock doesn't swell. We measure salinity test to measure salt concentration in rock for water, that's the method test what we apply. Now I'm showing you how we get the samples for these tests. This photo show, as I said, the rock cores should be cored from the ground using the rig. And this is actually Billy Bishop's site when we recover Georgian Bay Shale for the testing for this particular project. What is important for this lab test is that we have very good preserved rock samples. And we created some steps how to preserve it to be sure that the sample is preserved, that natural moisture content, and that can be actually usable for this kind of testing we developed for design of structures in the swelling rocks. So these are the steps, and tomorrow, if you are a geotechnical engineer and you're recovering your samples, you need to preserve. You need to send the samples for testing, swelling test. You have to follow these steps. These photos show some rock core samples. You see, this is a dry sample. We cut the sample to make a specimen for testing, but after 2 days of testing, you see it's useless. It's become just pieces of rock. This slide show the setup for free swell test and the presentation of the results. From these rock cores, we cut the sample and then we put these gauges to measure vertical swelling potential and horizontal swelling potential. Vertical is perpendicular to the bedding plane, while horizontal is parallel to the bedding plane. So we cut the sample like this, we submerge in water, and every day we measure with this deformation gauge, we measure change in strain. And the results are plotted here. We're doing that for 100 days. And then we get the average line between day 10 and 11. Actually, the slope of this line actually is that index, swelling index, what we're looking for. It's this one is vertical swelling potential, and these are showing the horizontal swelling potential. So, this is again, this is vertical to bedding plane, sedimentary bedding planes. This is parallel to. So this is a free swell test. We allowed sample to freely swell in all directions. The other test is semi-confined swell test, where we also have a sample and we submerge that sample in water, but the sample is stationary, and we put some frame where we apply some load. So we apply some pressure to this sample specimen, and then we monitor swelling strain, changes in strain. So these are the results. We also plot the results, swelling strain versus elapsed time in log scale. And this one is from free swell test, and this is for applied pressure of 0.3 megapascal. You see that swelling potential decrease or reduced when you apply some pressure on it. Later on, I will explain you what is the practical application of this kind of behavior. And the last test, swell test, what we perform, including this methodology, is Null swell test. This is the setup for Null swell test. Again, rock samples is here, specimen here, and then we put the whole ensemble of apparatus, which actually consists of load cell and these gauges. What we're doing here, we don't allow sample to swell. We actually, sample itself tries to swell and to push this, and we capture that push of that force on this load cell. With these gauges, we actually monitor that there is no movement, just the pressure. So the results of this test are presented here. And it's a natural scale, not a log scale. And this test doesn't last 100 days. It's much shorter. Actually, we're looking until we reach some equilibrium here, some plateau. In this case, that suppression pressure of this sample is 0.7 megapascal. So what does that mean? That this rock applies 0.7 megapascal on the structure, so which is huge. What does that mean? If you have a tunnel liner, you have to accommodate, you have to design your liner to this, then your liner is going to be very thick, very expensive, so nobody likes that. So once when we have these results, we plot these results in a graph like this, and we plot free swell test results. Then we put semi-confined swell test, tested with different applied stresses, and then null swell test results. And based on these results, we create this swelling envelope, which is used in design of these structures in swelling rocks. Later on, you will see how it's used in one of these methods for design. So here I just put some table, some summary of this data collected from different projects in Toronto. Once when you start with similar project like this, you can look at this table and you can get idea about the swelling potential in that area. But that could be done in the beginning of your project. But later on, when you going to design phase of your project, then you have to do site-specific investigation of swelling properties. This graph I also show just to show you how this salt concentration changed with time. You see, with time it's decreasing. This is the salt concentration in pore water of the rock, pore water in rock, and you see how swelling potential increase. And also, so it means that if we have higher salinity, it means that we have higher swelling potential. Okay. Then I also showed in the other slide where I'm showing that swelling potential versus calcite content, percentage of calcite content. You can see if the calcite content in this rock is higher than 14%, there is no swelling. So the rock will swell only if that calcite content concentration in that rock is low. Pardon me, is low. So that's but this is the balance between osmotic pressure due to salinity, high salinity, and this concentration of calcite content. That's why we measure these two properties as well on the sample before and after swell test. Now from these tests we have parameters and we have some methods for tunnel design in swell rock. One of the methods is Low-and-UN model, which is actually viscoelastic closed form solution for a concrete lined circle tunnel in swelling rock, which is developed by Dr. Low and UN in 1981. And in this model, the time-dependent rock structure interaction is characterized as a linear viscoelastic behavior through use of a single Kelvin element, employing time-dependent parameters obtained from the swell test. I will talk about this model a little bit more later. And the other method is actually Low and Hafni model for numerical analysis. So this is numerical, this is viscoelastic closed form solution. And this one is prediction with this model could be over-predicted, comparing with using this Low and Hafni model for numerical analysis. And in this, this model consists of 3 Kelvin units connected in series to model the nonlinear long-term swelling behavior of Crystal Shale. So what does that mean? After we finish these testing, laboratory testing, we have to provide some parameter which can be used on either of this Low and UN model or this Low and Hafni model. Kelvin model parameters for the rock structure time interaction analysis for Low and UN method could be estimated from semi-confined swell test results. And from these semi-confined swell test results, we can then get viscosity of dashpot in a Kelvin model for rock and time-dependent modulus of rock. And of course, this is the ratio of these two. So for the results from semi-confined swell test can be used in this method, Low and UN, which is closed form solution. While for the Low and Hafni model, swelling rock design parameters for numerical analysis could be obtained from the free swell test results and null swell test, getting this swelling potential in horizontal and vertical direction and suppression pressure. To use this for design, also it's necessary to know in situ vertical and horizontal stresses in rock, as well as Poisson ratio of rock and elastic modulus. So from these laboratory tests to proceed in design we of the tunnel, we have to get these parameters. For numerical modeling, we can use such a flex or flexes to analyze the swelling behavior of rock mass, as well as impact of that swelling on the tunnel lining. We have to have this design envelope. This is that envelope, what I presented before. This is free swell test results. This is pressure. So using this envelope and this equation here, we can predict strain changes and deformation and pressure on the structure in such a certain rock mass. The major for this application of this methodology, there are some misconceptions, and I want to explain that it is not a STEAM standard. So these are tests for rock swelling that have been used in 80s for investigation of swelling in many tunnels in Ontario, Canada, and other parts of the world. So it is not a STEAM standard. STEAM standard, there are some STEAM standard which deal with the swelling behavior, like D 45, 46, but it is for the soil, not for the rock, or C 1585, which is for the concrete, and this is a short-term testing, 10 days. So both of these STEAM standards are not applicable to rock formation in Southern Ontario because the swelling is long-term process. So if someone asks you to apply these standards to the rock, swelling rock, it's wrong. These standards are not applicable. And also interpretation of results. As I said, we have to use the second cycle, log cycle, to interpret the slope of the line, not the first and second. We actually discard the first from the day 1 to 10. We discard this data because specimen need to adapt to the new lab environment. So another question what you might be faced when you are, if you're a designer, tunnel designer, could be that if your tunnel goes through the different rocks. For example, this is one tunnel in Qatar, which goes through this kind of rock, 3 different rocks, and you see the swelling behavior is different in all of them. So the question is, which of these parameters you will use for your design? Are you going to design your tunnel to accommodate this swelling or this? That's something what you as engineer has to answer. So it's very important when you get the problem like this, a project like this, that you know that you make a good program or a testing program for your rock, and that testing program, of course, the scope of swelling test program depends, of course, of the type of the structure. Is it a tunnel? Is it a shaft? Whatever it is. Then depth of the structure and stage of the project. Then location of rock sampling from swelling test. Depends if the structure is tunnel or shaft. If you have a tunnel, then you have to do sampling and testing the rock at the crown and invert. These are vertical samples, and also at the spring line, these are horizontal samples. Then what kind of test you have to make a decision. Free swell test, do you need semi-confined, null swell test? Do you need horizontal design envelope or vertical design envelope? That's another point what you have to think when you're preparing testing program for your rock. How many tests we will test? That's the question. And where to test, from how many boreholes, where is the depth? All of this depends on heterogeneity of the rock at the site. So if you have homogeneous, of course, that you need less, maybe less tests than if you have heterogeneous like that one in Qatar. So, but at the end, a sufficient number of tests have to be performed. And I was talking about importance of the rock quality. We need to have a good quality of rock to be tested. For each of these tests, we need at least 30 centimeters of rock. So this is the good rock. This is the bad. This is the poor rock samples, and you can see the difference. You have seen this here. So once when you find out that your rock's well and you design, you've tried to design your structure, you can simply apply the pressure you find out, or if that suppression pressure is very high, then there are several methods of accommodating time-dependent deformation. One is to delay time between excavation and structure construction. This is the most common. The second one, this is the most common, but the problem is that if the construction schedule allows, but usually it doesn't, the construction schedule doesn't allow that, because they try to put the line right away after excavation, so that's the problem. The other method is maybe to install some compressible layer between the structure and surrounding rock. So between the rock and the concrete liner, you can put some compressible material like some kind of foam, styrofoam or something like that. And then it could be partially suppressed by external pressure using some rock anchors. So that's the situation in the semi-confined swell test. If you apply some pressure on rock, you decrease the swelling behavior, and you can create a stress relief between the structure and surrounding rock in specific case. So you can just make a gap between the rock and structure, so that you allow change in volume of rock, or could be a combination of all of us. So concluding remarks for this is that this methodology has been used in design of many tunnels with diameters of micro tunnel to 14.4 meters in Ontario and other countries. And the application of this approach has been found satisfactory. However, the requirement of methodology must be followed, and some omission of reduction of required items may lead to undesirable circumstances. So now I'm going to talk quickly about Billy Bishop Pedestrian Tunnel. So this is that tunnel which is built below the western channel. This is Ontario Lake. Actually, this is a man-made channel which actually divides the mainland from Toronto Island. These buildings here are Billy Bishop Airport. And before this tunnel, which is put in function in 2012, this ferry boat was used to transfer passengers from the mainland to the airport building. But then this tunnel is built, and the major issue for design and building this tunnel was that you see there is a small cover of above the crown of this tunnel. The tunnel was placed in Georgian Bay Shale, which is swelling rock, and this was the biggest tunnel ever built in Georgian Bay Shale. And also we didn't know what's happening here, because any drilling or investigation in this channel wasn't allowed. So the tunnel is 180 meters long. This is the main shaft. This is island shaft, and this is 35 meters deep. This is 30 meters deep, and the tunnel diameter was 12.5 meters. How the tunnel cross-section looks finally is like this. And this tunnel is very, very interesting because it's constructed using these sequences. First, these tunnel drifts, these 7 tunnel drifts were built. What does that mean? In the order as shown here in the numbers. So first was excavated this tunnel using this 1.8 meter diameter rock TBM, and then it was filled with concrete. And then they drilled this one, and all of them are filled with concrete. So this these drift tunnels actually created the umbrella or arch structure, which helped to prevent any collapse and from the top, because as I said, you know, the cover above this tunnel was less than 10 meters, and usually it has to be 2D. Tunnel is 12.5 meters. So after they finish this arch, they excavate this tunnel itself. And then after the excavation, they put this liner. How that looks, you can see on this photo. So this is the tunnel. This is that arch, these drift tunnels, drifts here. And this is the main shaft. You see how high it is. And this is the end of the tunnel. As I said, the tunnel is approximately 180 meter long. When we got this job, there was a GBR already done, so based on available investigation, but none of these swelling tests were done, or also that in situ stress measurement. So supplementary site investigation was performed, which to evaluate time-dependent properties of Georgian base shale, to evaluate horizontal in situ stresses, to verify subsurface geotechnical characteristics specified in geotechnical baseline report. The baseline report gives some parameters, but we use this supplement site investigation to verify it, and also to verify design approach and provisions made. So 2 boreholes were drilled, and one on the mainland and another on the island. And following that methodology I explained, the field test included in situ stress measurement and also Packard test for hydraulic permeability of the rock, and also all of these tests, laboratory tests I mentioned before. So, as I said, 1 borehole was drilled here, another one on the island, no boreholes in between. We weren't allowed, because we weren't allowed to disturb traffic in this channel. So this is stratigraphy with these boreholes. So the tunnel was placed in Georgian base shale. This is that Georgian base shale. These are the samples recovered from these boreholes, just as example. As I said, we did in situ.
Sorry to interrupt.
Yes.
Just a note that the students we should probably wrap up the presentation in 2 or so minutes, just so they have time to.
Okay. Okay, so we did in situ stress, we did in situ stress measurement, and we did strength properties, and also summary of swell. We did a swell test where we measured the swelling potential, vertical and horizontal. So we provide these parameters and create these envelopes to do prediction of deformation and prediction of deformation and predicted pressure in the liner, And you can see initially we assume that it's going to be 3 megapascal, but if they postpone construction of line in 100 days, you see it's reduced to 1.2. So these are parameters provided, and then this is the final outcome. The tunnel was built, and also these shafts. At the end, I also want to tell you guys that we have currently have a potential research project. It's Ontario Pump Storage Project, which consists on several tunnels and generating station placed in the Georgian Bay. This is in Northern Ontario. And in this project, during the low energy demand, the water from Georgian Bay will be pumped into this reservoir. And then during the high energy demand, it will be the water will be used on this generator and produce electricity for green electricity for Ontario. For this project, since this tunnel will be placed in Georgian Bay Shale, laboratory Swell test program is proposed, and it's going to be carried out in this GRC lab. So I just want to tell that I'm looking for the MH student who is interested to work on this project, and if anybody is interested, can contact me on this email. Using email, or you can ask Professor Bing for my contact. And so that's all I have today for you. So if you guys have any question, I'm happy to answer those questions.
Thank you so much for the presentation, Dr. Micic. We have time for maybe 1 or 2 quick questions, if anyone wanted to speak up. Not seeing any hands? Okay. I just have one curious one. You showed the Niagara tunnel photo, and I actually used that example for the rock mechanics class as well. But I was curious because you say that typically the swelling is most severe on the vertical, but in that photo of the Niagara tunnel, it looked like it was sort of potentially even off angle from the crown that was swelling.
Okay, so what's happening, usually it's like that, but not always. So here you're talking about this photo.
Yeah.
You know, the rock squeezed. This is not effect only on swelling. This is effect of stress relief. Right. You know, because this deep down, there is a very high horizontal stresses locked in this rock. Once when you excavate this, it just causes the movement, inward movement of that rock, you know. So this is not only swelling problem. What you see here, it's not only swelling problem.
I see.
Because swelling is time dependent. You need time to develop. This is immediate after TBM passed. After several days, this happened. I was in a tunnel, you know, at that time, and they have a lot of issues. That's why they decided to run away from this Kingston Shale.
Thanks. Excellent. Thank you so much. Yeah, please, another round of applause for our speaker today. Thank you for.
Thank you very much, and it was my pleasure to give this speech to the students.
Thank you, and hope you get better.
I need 2-3 days to stay at home, I guess, when you have COVID. Okay.